An introduction to limits. We're going to be talking about a graphical and numerical approach to limits, the ways that limits can fail to exist, one-sided limits, and piecewise functions and their limits. I'm assuming that you're watching this video on your very first lesson of calculus. And up to this point, you've used a lot of algebra and geometry to solve problems. And calculus is, in my opinion, the most useful branch of mathematics because it's the math that deals with things that are changing, like the volume of a balloon, the slope of a curve, or a rocket ship that is speeding up. And the most fundamental idea of calculus is limits, and limits allow you to look at what's happening in a very, very small region. So, what is a limit? So, here's a formal definition of a limit. I'm not going to read it to you. You can pause the video and read it. But this is the notation that you need to be familiar with. So, notice you've got the LIM, so that it means limit. And then underneath it, you have the X and an arrow and an A. So, X is approaching A, is how that's read. And then you have your function, f of x in this case, and that's equal to a number. So, the limit as x approaches A of f of x is equal to L, or whatever that L would represent, would be a number. And that's how you read that particular notation. So first, let's talk about determining limits from a graph. There are four basic situations we're going to look at. An easy situation with nothing strange going on, a graph with a hole and a point, and then limits that do not exist. So here's a situation where it's easy, nothing is strange is going on. And you'll notice that at this point right here, when x is 2, y is 5. And they're asking us, what is the limit as x approaches 2? So you want to talk about if you approach 2 from the left and you approach 2 from the right, what is the y coordinate doing, or what is f of x doing? Well, clearly it's just going all toward 5 because at 2 it's equal to 5 in this case. So the limit is equal to 5. Easy peasy. Now, if you have a hole, so here you've got another curve at 6 comma 7, you actually have a hole. But the limit, it doesn't matter what's happening at 6. It matters what's happening as you approach 6 from the left and the right. So as you approach 6 from the left, you're going towards 7. And as you approach 6 from the right, it's also going towards 7. So the limit here is also 7. Even though the function is not defined at 6, the limit is 7. Similar situation, but now we've got this point down here. So when x is equal to 4, the function is actually equal to 3. But if x were just to the left of 4, like 3.999, then it looks like the function is going to be very, very close to 5. And if x were just to the right of 4, like 4.0001, it looks like the y would be also very close to 5. So again, it doesn't matter what's happening when x is equal to 4. It matters for the limit, it matters what's happening as you approach 4 from the left and from the right. So as you approach 4 from the left and as you approach 4 from the right, the limit in this case is 5. So before we get to the fourth situation, I've been saying a lot of like from the left and from the right. Well, those are what's known as one-sided limits. So here's a very unique graph. As you approach 0 from the left, you'll notice that you just have this horizontal line at -1. So as you approach 0 from the left, you're going to be at -1. And as you approach 0 from the right, you're going to be a +1. So this is how we would indicate a one-sided limit. Notice you've got this little exponent that's just a negative sign. So that means as you approach 0 from the left. And so in this case, that's going to be, whoops, -1. We call that the left-hand limit. And then over here, when your exponent, this little superscript afterwards, the plus sign, that's your right-hand limit. So that's the limit as x approaches as x approaches 0 from the right. And so in this case, as you approach 0 from the right, you get 1. So for a limit to exist, the function must approach the same value from both sides, which is what we saw in some of our previous examples. Now, in this case, since the function is approaching -1 from the left and +1 from the right, the limit as x approaches 0, when you don't have a superscript behind it, that's like your overall limit, and that limit does not exist. So you can write the words does not exist, or you can write DNE, just the abbreviation, it's common usage. So here's an example. As we approach, here's our graph. We've got like a gap here, or a jump, and that we're looking for the limit as x approaches 3 of this function. So I'm looking at the left-hand limit, the right-hand limit, and then the overall limit. So the limit as x approaches 3 from the left, that's what that little negative sign means, that's going to be 5. The limit as x approaches 3 from the right is 8. So there are the four, since these are not the same, the overall limit does not exist. Here's another situation. The limit, we're looking for the limit as x approaches 1 from the left. So at 1, we've got the output is 1, but we've got a hole up there at 1 comma 2. Remember, it doesn't matter what's happening when x is equal to 1. It matters what's happening when x is approaching 1 from the left and from the right. So as you approach 1 from the left, it's 2. As you approach 1 from the right, it's 2. And f of 1 is 1. But the limit is 2. Since your left-hand limit and your right-hand limit are the same, that limit is 2. So this example was just to reinforce the fact that it doesn't matter what the output value is, the limit does not necessarily equal that output value. As long as your left-hand limit and your right-hand limit are the same, the overall limit is going to be that value. Here's another one. The limit as x approaches 0 from the left, 2. The limit as x approaches 0 from the right is going to be 1. F of 0, so that would be where your closed circle is, so that's going to be 2. And since your left-hand limit and your right-hand limit are not the same, that overall limit does not exist. Now let's talk more about limits that fail to exist. There are 3 scenarios where the limit can fail to exist. If the left-hand limit and the right-hand limit are different, which we've seen already, if your function increases or decreases without bound, or if your function oscillates between 2 fixed values. So looking in more in depth, like I've said, we've already seen this situation where there's a gap or a jump in your function, and that would be a situation where your limit, in this case, as x approaches -4, does not exist. This is a piecewise function. Here's an example of a situation where the function increases without bound. This is the function 1 over x minus 1 squared. You've got a vertical asymptote there, and as you approach 1 from the left and from the right, it goes toward infinity, and so that limit does not exist either. I should say the limit as x approaches 1 does not exist. Other limits in that function do exist. Let's take a look at example 7. Here we have a rational function, 1 over x plus 2, and we want to find the limit as x approaches -2. So I would recommend you graph this function in your graphing calculator. Here it is, y equals 1 over x plus 2, and we have a vertical asymptote at -2. Since you have a vertical asymptote, that means that the limit will not exist. As you approach -2 from the left, it goes toward negative infinity, and as you approach -2 from the right, it goes toward positive infinity, and so those are increasing and decreasing without bound. So that limit does not exist. The third scenario is if the function is oscillating between 2 values. So these 3 graphs are all the same function. I've just zoomed in a bit each time. So this is the graph of sine of 1 over x. And then this is just a table of values in case you're interested. But you can see that the limit is bouncing back and forth between -1 and +1. And if that's the case of a function, then that limit will not exist where it's bouncing. So here's an example, the sine of pi over x plus 1. So again, graph this in your graphing calculator. You're going to get something that looks a little bit like this. It might be a little bit uglier if you're using a T84 calculator, but that limit was not going to exist because it's bouncing up and down between 0 and 2. Now, finding limits using tables. Sometimes if it's too tedious to graph, you can also use a table. So here we're looking for the limit as x approaches 2 of x cubed minus 8 over x minus 2. So we want to find out, again, what's happening around x equals 2. So I would choose values that are getting closer and closer to 2 from the left, so 1.9, 1.99, etc. And then also looking at x values that are just to the right of 2 and getting closer, so 2.1, 2.01, etc. So first of all, if we plug in 2 into this function, you're going to get an error, or you're going to get undefined because you'll be trying to divide by 0, and thou shalt not divide by 0. So if you plug in 1.9 to this function, you'll get 11.4, and then 1.99, you get 11.94, and so on. And I would recommend definitely using the table feature of your graphing calculator to do this. So you can see that as you're approaching 2 from the left, these numbers, 11.4, 11.94, 11.994, they're getting closer and closer to 12. And just to confirm, as you approach 2 from the left, 12.6, 12.06, 12.006, those are also approaching 12. So we can assume that that limit as x approaches 2 is going to be 12. So here's a graph of the function. It's just a parabola with a hole in it, but the limit as x approaches 2 is equal to 12. So you'd have a hole right there at 2 comma 12 if you were to graph the function. Piecewise functions. We've seen a couple of piecewise functions so far. This graph here to the left is an example of a piecewise function. So here's an equation of a piecewise function. You've got a parabola when x is less than or equal to -2, and then you've got a line when x is greater than -2. We want to find the left-hand limit, the right-hand limit, and the overall limit as x approaches -2. Notice that the limit that we're looking for is the same as where these pieces break. So it's pretty easy to find the left-hand limit. You're just going to figure out which of these pieces would be to the left of -2. And in this scenario, it's going to be the top piece because anything that's to the left of -2 or less than -2 would be to the left of -2. So to find that left-hand limit, take the -2 and plug it into the piece. So if you plug -2 into that piece, that parabola piece, you're going to get 4. Oh, here's a graph of it. And if you take -2 and plug it into the other piece where x is greater than 2, that's going to be your right-hand limit because those numbers are bigger than -2. You're going to get 4. And the overall limit is then 4. And of course, I've already shown you the graphs or spoiled it a little bit, but the limit there is 4. Without graphing, try to find this limit. So the limit as x approaches 2. And again, with a piecewise function, you're going to have to consider the left-hand limit and the right-hand limit. So the limit as x approaches +2 from the left. So that's going to be, again, the top piece because that's where x is less than 2. And I will tell you that sometimes textbooks try to trick you and they want to put x is less than 2 on the second piece and x greater than 2 in the top piece. So make sure you're paying attention to your inequalities here. So the left, from the left would be anything to the left of 2 or less than 2. So when you plug in 2 to that piece, you're going to get 1. When you plug in 2 to the other piece, you're going to get 2. So since your left-hand limit is not equal to your right-hand limit, the overall limit does not exist.